lecture. So in the last class we had looked at how to solve an ODE, and I had mentioned that we'll look at some other means of finding out the inverse of the matrix. So let me take this particular code. Let me get rid of this cell. I don't need this cell as well. So let me get rid of all the A2s. We don't need the A2 bit. Alright, so let me quickly run this entire sheet again. So what we'll try to do first is to time this particular cell. So what does timing a particular cell mean? It means that it will tell us how much time it took for that particular cell to run. In particular, we are more concerned with this particular command. So let me not write time over here. Let me split this cell. So let me split this over here and let me split this over here. So let me run this cell first. Now before running this, let me do percentage time. So it will give me how much time it took for that particular cell to evaluate. It says 0 nanosecond because I've taken a very low grid count. So let me take 1000. Okay, let me run it. So it took 46.9 milliseconds to perform the inversion, and as as the number of grid points increases, so I've made it from 1000 to 10,000. So for 1000 grid points it took for let's say 50 milliseconds. Let's see how much time it takes for 10,000 grid points. This may take a while. If it's linearly scaling, it will take almost 5 seconds, or rather so it was 50 milliseconds, so it took 10 seconds, so it's not at all scalable. So then why is it not scalable? Okay, so before going into the scalability and all that thing, let me make n to be 6 just to show you how, again, just to show how a looks like. So let me just print a over here. Sorry, this should be a1. So a1 is said to be a sparse matrix, meaning most of the entries in A are zeros, and it's a diagonal sparse matrix, meaning most of the elements of A are concentrated around the diagonal. So now there are a host of different algorithms which exist for dealing with sparse matrices, and the fact of the matter is you don't really need that much of memory overhead or algorithmic overhead, because you're just keeping a count of elements which are non-zero. Okay, so A is like this. So let me do this. So let me import scipy dot, so let me import scipy as sp. All right, so sp dot sparse. So this is the name of the command, and let me dot csc matrix. So it's compressed. So what's the full form? So it's, we can simply have a look at the CSC stands for compressed sparse column matrix. So what it does is, instead of storing all the information, it will simply store the data, and it will store which row and column it belongs to. So it helps us in reducing the memory overhead. So I'll pass the numpy matrix A1 to this, and let me just assign it to AS, meaning A sparse. Let me then go ahead and print AS. So scip has no attribute sparse. Okay. thing we need to from SciPy import sparse. Yeah, okay. So this is how the matrix is stored, and just for your reference, I'll also print out what A1 was. So look, 0 0 is 1, 0 0 is 1, 1 0 is 1, 1 0 is 1, 1 1 is this. So there you go. It's a very efficient way of representing the matrix when other elements are 0. And the point is, once the matrix becomes larger, the number of zeros are going to grow by n square, by an order of n square, because most of the things lie on the matrix and lie on the diagonal, and the diagonal can be interpreted as being a line in an area, right? So as the size increases, the number of zeros increases quadratically rather than linearly. So why do we bother with converting to this CSC format? So once we've converted this, we can use the sparse matrix algorithms to find the inverse more efficiently. So let me import it. Alright, so we've imported the sparse.linealg module, and now we're gonna take a dot product. So AS is already of CSC format, so now we can write F equal to SL dot dot AS comma B. Sorry, so it should be AS dot dot B. So that's the way of achieving this dot product. Okay, so AS has an attribute, it's a CSC matrix, and it has certain, not attributes, but some additional functions associated with it, which include the dotting with a vector. Okay, it's not mentioned in this contextual help, but you can take a dot product with something like this. So AS dot dot will give you the required dot product, and so what we will do is we will take this bit of code, and let me copy this, let me comment out this old program, let me paste this, and let me see how much time it takes. So 10,000 was the number that we had used, so let me run this. So for 10,000 it took 10 seconds. Let me see how much time it takes. Let's say 667 milliseconds. So obviously the sparse solver runs much faster than the NumPy inversion, right? So so we forgot to take the inverse. Okay, so probably that's why it runs so much faster. I forgot to completely take the inverse. So sl.inv is the way to do the inverse. Okay, so let me run this now. So the benchmark was 10 seconds for NumPy. Let us see how much time it takes for SciPy inverse. Maybe it's not, or it took 11 seconds, so it took much more time. So it took the same amount of time, and it's not clear as to why this has happened this way, but should have happened faster, maybe for much more larger matrices. But something which will run faster will be the solver. So let me get rid of this. In fact, let me make it sparse. We need it to be sparse, and so there is a solver called as sl.spsolve. So spsolve stands for sparse solve. It lies inside the sparse.linear algebra submodule, and it takes inputs as the sparse matrix in CSC format and the matrix P. So let me run this. This should run much faster. Okay, so that took 690 milliseconds. So yeah, let us plot it and see whether it's fine or not. Oh, there's a bunch of errors. And what is the error? X and Y. So let me get rid of G. We don't need G for now. Yeah, okay. So with 10,000 points, everything matches quite well. Okay, let me reduce the number of points. In fact, let me increase it by a million, and there's a memory error. Okay, unable to allocate 74.5 GB. My PC is 32 gigabytes. So this is where C outperforms. You don't really need to worry. But if you define A to be originally a sparse matrix, you can avoid this error. So the fact is, I'm creating a numpy array out of this, and that it's initializing a whole bunch of zeros where you don't really need to initialize zeros. And once we do things in PETC, it will be clear how you can avoid this bottleneck. So PETC is much more efficient in this regard. I'm sure you could substitute or rather declare the A1 matrix to be a bunch of zeros. Rather than declaring them as a bunch of zeros, you could simply define it as a sparse matrix where everything else is zero by default. So let me dial it down. 1000. Yeah, almost 8 milliseconds. Plotted. Great. So let me make it 10 just to show that it is giving that old error that you imagine because of the first order nature of the boundary condition. So yeah, I mean, with this in mind, we go to the next part of this lecture, which is to use the inbuilt functions of SciPy to solve boundary value problems. So let us continue our journey. So again, I've created a new file. I've imported the usual things, and I've created the analytical solution of the problem that we had considered in the previous lecture. And the solution looks something like this. At x equal to 0, it is 1. At x equal to 2, the slope is equal to 0. So we made a nice finite difference program, and we were able to solve it. And once we've done that, we were able to show how we can implement a second order solution with the host node. So now we're gonna use the inbuilt function of SciPy to solve the ODE. So first things first, let us import, or rather from scipy dot integrate, let us import solve BVP. So like solve IVP, there's another function called a solve BVP. It stands for solve boundary value problem. Alright, so let me import this. So what does this function contain? So let us have a look at the contextual help. So it takes as an input the function, the boundary condition, the X array, that is the domain, the Y, which is a solution array, P stands for parameters, function Jacobian, boundary condition Jacobian, tolerance, max nodes, verbose, blah blah blah. So function is callable. Okay, so let us create the function. So def function, and it will take inputs as X and Y, and it will return something. So let us go to the previous program, right? In fact, let me show you what the equation was. It was d2f dx2 equal to f. So we have to first split the problem two into a series of first order equations. So let me, instead of f, let me call it d2y naught dx2 equal to y naught. Let dy naught dx be equal to 1. This implies dy1 dx equal to y0. And there's a very simple splitting of the equation, this particular equation, into these two particular equations. Alright, so we have to return what? Y1 and y0. Fine. So I will go over here. I will return y1 and I will return over here y0. Alright. Now I have to define what? I have to define the boundary condition. So define the boundary condition. So here the boundary conditions are implemented as ya and yb, where a, b are identified as the sort of endpoints of the domain. So the inputs to this will be ya, yb, and I will return the following. So the boundary condition was y0 equal to 2, y prime or rather y0 was equal to 1 and y prime 2 was equal to 0. So ya is equal to 1 essentially, and yp prime is equal to 0. So the way to implement this is we have to give the residue. So I must give over here ya0 minus 1. So 0 stands for the Dirichlet, and here it will be yb1 minus 0, which stands for the Neumann condition. Alright, so after this we must create the domain. So xi, that is the or xd, discrete domain, is np.linspace 0 to 2, and let me take 10 points, and y approximate will be np dot zeros. There will be 2 rows and the number of columns will be the size of xt, that is the domain. So it will be simply xt dot size, and this also works fine. Now what we will do is we will call the function. So residue of this function, let me call it res, solve bvp. We will pass the function, we will pass the, so what did we have to pass? Let me, function boundary condition xy, function boundary condition xy. So yeah, that x has an initial guess, and that's pretty much it. So let me run this to see if there's an error. There's no error. So now what does res contain? Let's see if we can have a contextual help on it. So x contains all these things. Essentially it treats it as an optimization problem, which is fine. Okay, so let me print res over here. So what does it contain? Iterations, xp array, yp array. So yp is a double array. Yeah. Sol. So we are more interested in sol. Sol is the interpolation object, and I think we have used this previously as well. Whenever you have access to an interpolation object, might as well use that interpolation object. So how do we go about using it? So I will create a new grid. So x interpolate will be np.linspace. This will be min of it will be the minimum of xd to maximum of xt, and I will take 1000 points. So then yi will be equal to the residual times the sol, but now that has to be evaluated over xi. Alright, so now with the help of this we can simply plot xi comma yi. Oops, there's some error. Okay, we just need the residue of the first function, that is we need the solution for y0, because remember y0 was the original function and we made an auxiliary function y1 to split this into a series of first order equations. So we are more interested in y1. So let me plot this. Boom, there you have it. This is the solution that we were looking for. In fact, because I have yi, I can also get the yi derivative, which will be what? Res sol xi 1. And I can go ahead and plot the derivative as well. Mm, yeah, it's an issue with the literal string because let me use this instead. This should work. Yeah, so then let's just plt.legend and plt.axh line at 0. So look, at x equal to 2, the slope becomes 0. So with the help of this, we are able to solve the problem in a relatively short manner, and I've showed you how to implement the boundary condition. The boundary condition has to be implemented as in the form of a residue. Okay, it sort of acts as a constraint to this optimization problem. So yeah, let us do one more problem. Let me, so we don't need this anymore. Let me paste this over here. Let us solve this problem. So y double prime plus 2y prime minus 2y equal to minus 3. y0 will be equal to 1 and y2 will be equal to minus 2. So this second order differential equation, ordinary differential equation, 2-point point value problem. And because we've developed the program before, it's quite easy for us to implement this. So let me make it y naught, right? And I can write y naught prime equal to y1. This becomes y1 prime plus 2y1 minus 2y0 equal to minus 3, and these are still the boundary conditions. Alright, so it will still return y1. Over here it will return 2y0 minus 2. So essentially this is y1 prime equal to 2y0 minus 2y1 minus 3. So it's 2y0 minus 2 times y1 minus 3, and the boundary conditions are 1 and minus 2. So it's already 1, and over here, because it's not a Neumann condition, it's a Dirichlet condition, it was minus 2, so this has to be plus 2. So the residue, so the way of writing this boundary condition is yb plus 2 equal to 0. So yb becomes minus 2 at the other boundary. The domain does span from 0 to 2. Yeah. So yeah, let's solve this and see what happens. So this is how the solution looks. We don't really need the horizontal line. Yeah. So this is the solution of the problem, and this is the derivative in case someone is interested. So yeah, you can do problems like this. Just have a look at the function reference for solve BVP, and yeah, it clearly says it solves a first order system of ODEs like this, subjected to 2-point boundary conditions like this, right? So things become much easier when things are inbuilt, but even when they are not inbuilt, you can write your own program. It's not that difficult to implement really. It's just a matter of getting used to. So with this, let us conclude this particular session. I'll be back next time with regular perturbation. We will proceed to singular perturbation, and let's see how we can progress from there. With this, I wish you a good day. I'll see you again next time. Bye.